I'm going to be going over a PCB that I simulated and designed for the power systems of a robot that I performed research on. So here's an overview of the specifications of the PCB. So the design needed to power two propulsion motors that could operate at varying speeds, so we needed to use pulse width modulation, and it also needed to have bidirectional current flow, so forward and reverse, which required the use of an H-bridge. These motors were rated at 7.4 volts and had a current draw up to 15 amps. There was also a conveyor motor that was used to collect trash. So this was a water cleaning robot, and it needed to have the capability to remove trash from the water. This motor was rated at 5 volts and had a current draw of up to 750 milliamps. The microcontroller and Raspberry Pi to control the robot also needed to be powered by this PCB, and these are both rated at 5 volts, and combined will have less than 1 amp of current draw. The entire PCB will also be powered by one lithium-ion battery rated at 7.4 volts, which is also the voltage of the motors. So my H-bridge I designed to have two high-side PMOSs and two low-side NMOS MOSFETs. I also chose to implement sign magnitude drive logic, which I will go over in the next slide. And then also I will be discussing the creation of an NPM Totem-Pole MOSFET driver and some RC delay shoot-through protection for the H-bridges. So we can see in the pictures on the right that the red line represents forward, so the top left PMOS and the bottom right NMOS will be turned on. And then in reverse, the top right PMOS and the bottom left NMOS will be turned on. And this will allow that bidirectional current flow. In the off state, the two bottom NMOSs will stay on, and this will allow the current a path to dissipate when there is no voltage being applied through the H-bridge. And because the motors act like inductors, there needs to be some path for this current to dissipate in the off state. So this is the sign magnitude drive logic that controlled each of the H-bridges. So my goal was to only control these H-bridges with two input lines coming from the microcontroller. So this would be the PWM X and the direction Y as seen in the truth table. So because there's 2 bits, there are 4 different states that it can be in. And one of these has to be reverse, one of them has to be forward, and the other 2 were set to be off. So the N1 and N2, the two low side NMOSs, needed to be on in the off state. And then, like I went over in the previous slide, the top left PMOS and the bottom right NMOS will be turned on for forward, and the top right PMOS and the bottom left NMOS will be turned on in reverse. So based on this truth table, I was able to derive an expression for the left side and the right side of the H-bridge, and that can be seen in the equations near the bottom. So both P1 and N1 will be X and Y knotted, and then P2 and N2 will be X and Y knotted. So these represent a NAND gate. And there are a couple inversions that happen in the circuit, so it actually cancels out and returns to being a NAND gate. So we can see in the picture on the left that this is the final logic that was implemented. So the top NAND gate will feed into the left side of the H-bridge, and the bottom NAND gate will feed into the right side of the H-bridge. This is the MOSFET driver that I implemented. It's referred to as an NPN Totem-Pole configuration, and it basically is used just to step up the voltage. So there's only 3.3 volts coming as an output from the microcontroller GPIO pins, and as we can see in the diagrams on the bottom left, the left one is for the N-channel MOSFET and the right one is for the P-channel MOSFET. If we only apply a 3.3 voltage to the gate of the MOSFET, it doesn't supply enough current that the propulsion motors need in order to be amply powered. So What this NPN Totem-Pole MOSFET driver does is it will step up the 3.3 volts and it will bring it to 7.4 volts. So the way that it works is this bottom NPN has a pull down resistor, so it'll be turned off by default, which means this NPN, which has a pull up resistor, will be on. So when the microcontroller is in reset state or when the microcontroller is outputting a 0, this output will be high. In contrast, when this microcontroller output is, or input is high, this NPN will be turned on, and this will have a path down to ground, which means the output of this MOSFET driver will be low. So this is the resistor capacitor delay shoot-through protection that I implemented for the H-bridges. It ensures that both transistors of one side of the H-bridge are not on at the same time, which would short them with the battery, and it can possibly destroy the MOSFET. So it's important that this doesn't happen. It functions based on this Schmidt inverter, which has a hysteresis in it and has very specific points where it begins to invert, and in an undetermined state, it will hold its value. So we can see this timing diagram that I created on the right here. So there are a couple inversions that happen through the circuit. So I'm basically just trying to follow the signals. And then based on the fall and rise times that were presented in the data sheet of this top chart being the N-channel MOSFET and the bottom chart being the P-channel MOSFET. So based on these numbers and the timing diagram, I was able to determine that the NMOS needed roughly 5.5 microseconds of delay and the PMOS needed 2.2 microseconds of delay. So now we're going to be looking at the H-bridge simulations to show you some of the results that we're looking for. So this is the complete simulation for the H-bridge. So I was able to obtain the models for the PMOS and NMOSs from the manufacturer's website. I also have the RC delay shoot-through protection here with a Schmidt inverter. So the diode is going in this direction for the NMOS circuitry because we only want the falling edge to be delayed, and in the reverse for the PMOS circuitry, we only want the rising edge to be delayed. So the orientation of this diode is important. We also have the NPN Totem-Pole MOSFET drivers here and the logic that is used to drive the H-bridges known as sign magnitude drive. So let's look at some of the simulation results. So from here we can see the Vout plus minus Vout minus, which is the voltage across the motor terminal. We can see based on basically going through the different combinations of the truth table that it can have both a forward 7.4 volts across it and a negative reverse 7.4 volts. So it is able to have bidirectional current flow. We can also see in these blue and red lines. So the blue line represents the PMOS and the red line represents the NMOS. So we can see that the PMOS starts to rise a short duration before the NMOS starts to rise, and the NMOS starts to fall for a short duration before the PMOS starts to fall. So basically what's happening is the PMOS is turning off right before the NMOS turns on, and the NMOS is turning off right before the PMOS turns on. So this ensures that both transistors on one side of the H-bridge are not on at the same time. This is the other circuitry of the PCB, and this contained all the 5-volt components. So the microcontroller and Raspberry Pi that needed to be powered with these JSTs, the conveyor motor which was rated at 5 volts, and the relay coil which actually ended up not being on the final PCB due to the fact that it was a latching relay instead of a non-latching relay. But this conveyor motor was implemented using a high side switch and a PMOS. It also had the voltage step up again from the 3.3 volts to 5 volts, and this again used that NPN Totem-Pole MOSFET driver. The conveyor motor also had a flyback diode that allowed the current to dissipate once the PMOS was turned off. So we can see there's also some capacitors here on both the input and output side of the linear regulator, and this just smoothed out the signal on the input and output side. So now that all the design considerations were taken into account and they were simulated, it was time to actually build the PCB. And I built my PCB using Eagle Autodesk, and I'll be showing you some of those designs now. Here is the Eagle schematic that I created for the PCB. So we have our H-bridge here, the MOSFET driver circuitry, the Schmitt inverter RC delay shoot-through protection, and then another circuit just mirrored down here. It's identical, so there's two of them for two propulsion motors. Here we have a 4 2-input NAND IC chip, as well as an inverter, a couple JSTs here for the microcontroller input logic. And then we have our battery terminal. We have the conveyor motor circuitry down here with the high side switch and the flyback diode here. We have the linear regulator. We also have the relay here also with a flyback diode, a switch to control the 5-volt regulator, whether or not it gets power, as well as whether or not the coil of the relay gets power. We also have a couple fuses here, so a 35 amp fuse on the battery to ensure it does not exceed that, as well as the H bridges, which have a 15 amp fuse on them. This part of the design also needed to be done in conjunction with a component supplier such as DigiKey or Mouser. I decided to use Mouser, and I found all the components on their website and the corresponding symbols and footprints for the different components. So now we're going to go to the actual board design through Eagle. Here we have our Eagle layout with all the component footprints as well as the traces running between them. So just to go over some of the parts here, we have our two H bridges right here with the motor terminal, the large capacitor, and the 4 transistors. We also have the battery terminal, the relay. I also decided to put all the 5-volt circuitry and components together, so the conveyor motor as well as the Raspberry Pi microcontroller JSTs. This is our NPN Totem-Pole step-up logic going 3.3 to 5. Over here we have all of our step-up voltage for the H-bridges as well as the RC delay shoot-through protection, and it's mirrored down here for the other H-bridge. Here we have a couple logic IC chips and the microcontroller JSTs. I also had a lot of freedom when designing this board with regard to part placement, so I tried to make the traces as short as possible. I also had to make the traces the right width according to a width calculator that I'll show you. But basically all these small signal, low current traces only needed around 10 mil, but I decided just to use 15 to be safe. Also, these larger traces needed much larger widths for each of the H bridges, and the current that is coming from the battery needed even larger traces. There's also a lot of these vias coming through on these large current traces, and this is known as via stitching. So as you can see, this is the top layer. On the bottom layer, the traces, these high current traces, are actually mirrored with one another so that the current can travel on both the top and the bottom of the board. So there's 2-ounce copper on top and 2-ounce copper on the bottom, a 2-layer board. And so this allows enough current to travel through each of the propulsion motors. I also have a few holes drilled into here for screws in case the board needed to be mounted, and various text labels for each of the component parts and the pins of the JSTs. Once I was happy with the way this looked, I generated the Gerber files and ordered my PCB through PCBWay. In order to calculate the appropriate PCB trace width, I used DigiKey's width conversion calculator. So the propulsion motors needed 15 amps, and with a 2-ounce copper layer on both the top and bottom, this essentially becomes 4 ounces of copper. And with a 25 degrees Celsius rise, which is possible because of the heat sinks, the minimum trace width needed to be 184, so I roughly did 200 mil. And for the battery traces going into the H bridges, the current can go up to 35 amps. And again, 4 ounces of copper, 25 degrees Celsius rise. The minimum trace width needed to be almost 600 mil, so that is roughly what I went by. For the via sizes, I used Saturn's PCB Design toolkit, so just entering general values of 25 mils for the via hole diameter and 50 mils for the internal pad diameter, I can see that the via current is about 3.25 amps, and so I use this standard via size for almost all the vias on the board. So with the via stitching, just placing multiple of these along the trace, this would dissipate enough current through the vias. So once the PCB itself was ordered and all the components along with them through Mouser were ordered, it was time to write some of the code for the microcontroller that would control this PCB. So there are 7 signals that need to go into the board, and these can be controlled by the microcontroller GPIO pins, the general purpose input-output pins. And so this needed to be what I labeled as in 3, which would just turn the conveyor motor on and off. The ground, which will just be the common ground between the microcontroller and the PCB. The 3.3 volt power output from the microcontroller. There are also these 2 signals that control the H-bridges themselves. So each H-bridge has 2 signals that we went over in the sign magnitude drive. So the in will determine whether or not the current is forward or reverse. So if it's high, it's forward, or if it's low, it's reverse. Also the pulse width modulation. So this needed to be set to a value of 0 to 99%. I chose to set my PWM frequency to 5 kilohertz. I'll show you some of the code that did this, and it also needed a minimum value of 15% in order for the motors to start turning. So let's take a look at some of that code. This is the code for the microcontroller. It was written in C in Code Composer. We have the main function here, which basically goes through different sets of tests that I have a video on I'll show you. It will set the motor direction current to be forward or backward. It can also go through different pulse width modulation, duty cycles. Here we have the motor.c file, which initializes the 2 PWM signals. So it sets 2 alternate functions of 2 GPIO pins using the API built into the microcontroller. So here we're setting the frequency to be 5 kilohertz, various other things with the timers. We also have a set motor speed function that will set the pulse width modulation duty cycle. We have a function to initialize the motors, so the in1 and in2 of the motor, the propulsion motors, as well as the in3 of the conveyor motor. So this is the direction, or with the conveyor it's an on and off. We have the stop propulsion motor, so this will just set the PWM to 0. A function to turn the conveyor on and off, set the propulsion motor direction, and a delay used for testing purposes. And that's basically all the code. So now let's look at the final product and run a test on it to see how it works.
So here we have the fully constructed PCB. So over here on the left side we have the 2 microcontroller JSTs that basically control the PCB. We have 2 sides here, one for each motor. The logic is mirrored. These microcontroller JSTs, the signals feed into this small inverter and this 4 2-input NAND to basically control the logic. This is a Totem-Pole BJT configuration that steps up the voltage from 3.3 to 7.4 volts. This then gets fed into this RC delay circuit with diodes and these 2 Schmitt inverters for the shoot-through protection. These signals then feed into these 2 high-side PMOSs and 2 low-side NMOSs that make up the H-bridge. There's 2 motor terminals here, one for each propulsion motor, 2 big 1000 microfarad capacitors, and some smaller 0.1 microfarad capacitors just to filter out the signal. So those are our H-bridges here. Over here we have the 5-volt circuitry. So here is the motor terminal for the conveyor belt. We have the 5-volt regulator here with a switch that can turn it on and off. A couple 10 microfarad capacitors to filter out that signal. We have again some logic here to step up the voltage from 3.3 from the microcontroller to 5 volts so that we can power this high side PMOS switch. We have two JSTs here that will power the microcontroller and the Raspberry Pi. Over here we have the battery terminal. So this is ideally 7.4 volts, which is the voltage of the propulsion motors. We have a 35 amp fuse here and two of the 15 amp fuses here to protect both H bridges. So that's just some additional protection. And as you can see, there are heat sinks on all the MOSFETs as well as the 5-volt linear regulator, because those tend to get a little hot when they're drawing a lot of current.
So here we have some of the data that I collected from an oscilloscope testing the PCB. So I just wanted to look at the RC delay shoot-through protection, extract the data, and then plot it on MATLAB to see how it looked. So I tested it at two frequencies, 10 kilohertz and 5 kilohertz, and we can see the delays for both are about the same. So the blue line, which is the PMOS, and the red line, which is the NMOS, we can see on the left side that that rising part has a delay of about 5.4 microseconds, and the falling part has a delay about 5 microseconds, which is very close to what we designed it to be. So here's some of the pulse width modulation results that I also collected using an oscilloscope while testing the PCB and then plotting it in MATLAB again. So I tested 4 different cases at 10 kilohertz. We can see in the top left there that motor 1 was set in reverse at a 25% duty cycle, and motor 2 was set forward at a 50% duty cycle. You can see on the y-axis there, representing voltage, that the current is actually going in opposite directions. If you'd like, you can pause this video to look at the other 3 cases. The last part of this project was designing control systems to be implemented on the microcontroller with various algorithms to have the robot, once it was fully built, intercept objects and be able to pick up trash at various locations. So let's take a look at some of these simulations. So here we have the control simulations that were designed in Simulink of MATLAB. We have a few input parameters here in the shaded blue region. So these can be variable depending on the robot's thrust capabilities, its mass, its length and width, also its initial X and Y position in the coordinate system, and its orientation represented by theta. In this other blue shaded region, we can also simulate the effect of the drag force of water current, so we can set the speed of the current and the angle that it's coming at. So this diagram here shows the robot's global coordinate system. So gamma represents its current position, so this could be something that is determined by a GPS or IMU. Theta represents the robot's current orientation, so this could be determined from something like a IMU or magnetometer. And also beta, which is its correction angle to return to the target, which is always located at the origin in this simulation. So let's briefly glance over some of the algorithms that are used within these function blocks. Here is the calculate thrust function block. So this just deals with forward and backward acceleration. So based on the robot's current velocity and position and its distance to the target, it can calculate the appropriate thrust. So here we have the calculate orientation function block. So this just deals with the angles such as gamma, beta, and theta. And based on its orientation towards the object as well as the moment arm of the robot, it can calculate the appropriate adjustment angle. And it can do this at varying speeds based on the robot's previous angle and the magnitude of the change that needs to happen. So this acts as sort of a PD controller to correct the angle. Here we have the sum forces function block. So this deals with the drag force produced by the water current, and it also deals with the forward and backward acceleration based on the robot's current orientation, and sums up the various forces in order to determine the new position based on a double integral from acceleration. Here we have the conveyor function block, and this just determines whether or not the robot is close enough to the target to activate the conveyor and pick up the object. So let's set up and start the simulation. I'm going to be setting the water current to 1 meter per second at a 270-degree angle, so straight downward, with these various initial parameters. So it'll be starting in the upper right-hand quadrant, just like this picture. Here we have the results of the simulation that we just ran. So we can see on this XY plot that the robot started in the upper right-hand quadrant, and it was initially facing straight upward at 90 degrees. Because of the water current going straight downward, its movement was initially down, and its initial movement was to correct beta. So it turned towards the target and tried to keep beta at 0 throughout the duration of the simulation. We can see gamma as the XY position of the robot changed. These sharp spikes are happening when the robot switches quadrants, and we can see also the XY velocity and acceleration in either direction. Based on this XY plot, it looks like the robot passed the object initially, but then fought upstream in order to intercept it, and we can see that with this pickup graph that shows that there were a few periods in time where it was close enough to pick up the object, but then it reaches a steady state where it holds its value and beta is maintained, which means it is constantly orienting itself toward the object. So in conclusion, we implemented sign magnitude drive logic for the MOSFETs of the H-bridges to allow only 2 GPIO pin outputs to control the H-bridges. We also implemented RC delay shoot-through protection to ensure that the PMOS and NMOS of one side of the H-bridge is not on at the same time, which could damage the circuit. We also implemented an NPN Totem-Pole MOSFET driver to step up the voltage to the gate of the MOSFETs to ensure that the transistors have enough current going through them to power the motors. We also have circuit safety protection with the via stitching, where the top and bottom traces of the PCB are mirrored, so that allows for higher current flow. We have fuses that ensure that in case the propulsion motors become rotor blocked or something were to short, that the circuit will shut down. We also have heat sinks on the MOSFETs in the 5-volt regulator to ensure that when the current through them is high, that they do not overheat. With all these design considerations, we do have complete control of speed and direction of the propulsion motors. The robot can be fully operational with only one power source. And with these control simulations, we were successful in allowing the robot to intercept an object at any given distance and angle with variable size, thrust capabilities, and water current speed and direction. And that's it. Thanks for watching.